Welcome everyone to this explainer. Today, we're jumping right into what I like to call the game of odds, and we're going to decode how the genetic lottery actually works. If you've ever wondered how certain traits get passed down from generation to generation, or why a trait might skip a generation entirely, you are in the right place. We're going to break down the mechanics of inheritance and make the complex math of biology incredibly clear.
Here's our roadmap for today. We'll kick things off with the rules of the genetic lottery. Dive into autosomal dominant and autosomal recessive inheritance, check out the sex-linked twist through X-linked dominant crosses, and finally, decode your genetic future.
All right, Section 1, the genetic lottery. Let's set up the game board and define our playing pieces.
So, the fundamental playing piece in this game of odds is the allele. Basically, an allele is just a specific version of a gene. Think of it kind of like a lottery ticket, but you don't get the whole ticket from one place. You get one allele from your mother and one allele from your father. And how those two pieces interact, that's what ultimately determines your final traits.
Now, that interaction brings us to a super important distinction we need to keep in mind throughout this explainer: genotype versus phenotype. Your genotype is essentially your hidden hand of cards. It's your actual genetic makeup, usually written out as letters, like a capital A and a lowercase a. You literally can't see this just by looking at someone. The phenotype, on the other hand, is the physical result. It's how that hand of cards actually plays out in the real world, whether a person is physically affected by a disease or totally unaffected.
Moving on to Section 2, autosomal dominant inheritance. Let's look at the heavy hitters of the genetic world.
Okay, looking at a classic autosomal dominant cross, the core rule is pretty simple. Just one allele can cause the disease. Here, the dominant allele, that capital A, is the carrier. We've got an affected female with a genotype of big A, little a, crossed with an unaffected male who has two little a's. Because the trait is dominant, she only needs that one big A to have the affected phenotype. So when we map this out on our Punnett square, drawing the alleles down and across, it gives us a really clear picture of the final odds. Breaking down that Punnett square reveals a clean 50-50 split. Half the offspring, represented by that big A, little a genotype, will be affected by the disease. The other half get the two little a's and are completely unaffected. It is literally a straight coin toss for every single child they have.
All right, Section 3, autosomal recessive traits. What happens when traits get a bit sneaky?
The rules have shifted a bit here. Notice that for recessive traits, you actually need a matching pair, two lowercase b alleles to express the disease. In this scenario, we have a cross between an unaffected female and an unaffected male. But check out their genotypes. They're both big B, little b. They are carriers. They carry the disease allele, the little b, but that common big B dominates and keeps them perfectly healthy. When they pass their alleles down into the Punnett square, though, things get pretty interesting. We end up with a highly predictable set of probabilities. From two totally healthy parents, we get three different genotype outcomes. There's a 25% chance of the child being big B, completely unaffected, not even a carrier. Then there's a 50% chance they'll be big B, little b, meaning they'll be just like their parents, healthy but carrying the gene. And finally, there's a 25% chance that those two recessive little b alleles link up, resulting in an affected child.
So let's think about how this translates to the phenotype, what we actually see. Let that math click for a second. If we combine the non-carriers and the healthy carriers, even with two carrier parents, any child has a massive 75% chance, 3 out of 4, of walking away with a completely disease-free phenotype. The odds heavily favor a healthy outcome, which is exactly why these recessive traits can hide in family trees for generations before two carriers happen to meet.
Next up, Section 4, the sex-linked twist. Because yeah, biological sex absolutely matters here.
Up until now, biological sex didn't really change our odds, right? The chances were exactly the same for sons and daughters. But what happens when traits ride along on our biological sex chromosomes?
Well, here are the new rules for this phase of the game. Sex-linked traits are tied specifically to the X or Y chromosomes. Since females typically have two X chromosomes and males typically have one X and one Y, the inheritance patterns completely change. X-linked traits can affect both males and females, though often in different ways. But because the Y chromosome is exclusively male, Y-linked traits only ever affect males.
Section 5, X-linked dominant crosses. Let's look at how this plays out in a few scenarios.
In our first scenario, we've got an X-linked dominant disease. The capital A on the X chromosome is the culprit here. We're crossing an affected female, who has one diseased X chromosome and one standard X chromosome, with an unaffected male who has a standard X and a Y. Let's see how these combine.
This perfectly illustrates how balanced things can actually be in this specific setup. The odds fall completely into quarters across the board. The mother has a 50-50 chance of passing on that affected X chromosome to any child. So we end up with a 25% chance for an affected female, 25% for an unaffected female, 25% for an affected male, and 25% for an unaffected male. Everyone gets an equal shot in this particular genetic draw.
But look what happens when we swap those starting conditions. Now we have an unaffected female, meaning 2 common X chromosomes, crossed with an affected male. His one and only X chromosome carries that dominant disease allele, the big A. Now think about how a male passes on his sex chromosomes.
This is where the twist really hits hard. A father has to pass his Y chromosome to his sons, and he has to pass his X chromosome to his daughters. Because this father's only X chromosome is the affected one, it goes to all of his daughters, meaning 100% of the females will be affected. Meanwhile, his healthy Y chromosome ensures 100% of the males are completely unaffected. Looking at the total offspring, it's still a 50-50 split, but it is entirely divided by biological sex. This is a massive departure from those standard autosomal rules we looked at earlier.
Finally, Section 6, Decoding Your Genetic Future. Let's tie this whole thing together.
So, to summarize everything we've mapped out in this explainer today, if a trait is autosomal dominant, it only takes one allele to show up, regardless of sex. If it's autosomal recessive, it needs 2, which means perfectly healthy carriers can hide the trait for generations. And if it's X-linked dominant, it only needs one allele, but those inheritance odds shift dramatically based on biological sex depending on which parent carries the trait.
Mapping all of this out drives home a pretty powerful realization. Genetic inheritance isn't just random magic. It's predictable fractions and probabilities. Which leaves us with a really vital question to ponder. How can we use the knowledge of these very real odds to make informed, empowered decisions about our families and our futures? Understanding the game board is just the very first step. Thanks for exploring the game of odds with me on this explainer. Keep questioning and keep learning.